first derivative, so you should be able to set it equal to 0. Getting a GCF out is probably going to help you. There's what the sign charts should look like if you're doing it right. Which I'll show in just a moment. So remember, the idea of the second derivative test, finding concave up, concave down points of inflection, is going to be the same idea as the first derivative test. You're going to do the same steps. You're going to set that second derivative equal to 0, and then you're going to use those as points to make a chart to figure out where it changes direction, that derivative changes direction from positive to negative. Except this time, the positive is going to tell you it's concave up, the negative is going to tell you it's concave down, and if it changes direction, that point will be a point of inflection. That's the idea here. So if you're factoring that, you should get -3/2 and -2. And there's what your sign chart should look like. That's all review. That's stuff we did before break. So that means we are increasing from -∞ to -2, union with -3/2 to infinity. And we are decreasing in the space in between from -2 to -3/2. One of these is a max, one of these is a min. Which one? Because? Right, if you're increasing, switching to decreasing, going up and then hitting a peak, maximum, and then going back down. And then minimum will be the opposite way. You'll change from decreasing, going down, to going up. Or the first derivative is changing from negative to positive. So our maximum is at -2. And then we plug in for y to get an output. And our minimum's at -3/2. Again, we plug in for y. So then we're going to do the same thing for the second derivative. I'm going to give you a moment to do that. And make sure we're finished up here. probably say you'd get a calculator to get the y coordinates here. But concave up, where the second derivative is positive. And concave down, where the second derivative is negative. So there are our intervals. And that's our process. Good so far. Questions on that? Okay. I want to actually connect this here to a visual of what this looks like. So here is your graph. Here's what the graph looks like. You'll notice it goes increasing and then decreasing and then increasing again, just like our sign chart says it should. And if I zoom in here, -2 and -3/2 are very close together. So it should make sense that we're packed in pretty close together here. So I'm going to zoom in a little bit so that we can see the points of interest here. And you'll notice that -7/4 is actually kind of exactly halfway in between -2 and -3/2. That doesn't always happen, but it does happen in this case since we have a cubic function. So here is our maximum. It's a relative maximum and a relative minimum, because then it goes, because from the maximum, then it hits a minimum, then it goes to increasing again. And this goes to decreasing. So there's our max, there's our min. And then here is our inflection point, where we're changing from going concave down, and then we hit our inflection point, and then we're going concave up. I said yesterday, concave down is a frowny face, and concave up is a happy face. So we're increasing less and less and less and less, and then we hit our maximum, and then we start decreasing, and we decrease a little more and decrease a little more, and then, inflection point. And after that, we're decreasing. We're still decreasing, but now we're decreasing a little bit less because now we're concave up. Decreasing a little bit less, hit our minimum, start increasing more and more and more. And I just want to connect this. That's what the original function looks like. And from there, you should be able to get a rough idea of what the first derivative looks like. The first derivative should look like, it should be positive for a while, and then hit a point here where it's 0, and then be negative, and then hit a point where it's 0 again, and then go back to being positive. It shouldn't be negative for very long, but it will be negative, and then it's going to be positive and get pretty big fast, because this is a pretty steep slope as we get to the right of 0. So here is what that derivative actually looks like. And hopefully you know that it should look like a parabola because it was an x squared function. Here is that derivative. Hey, look, -2 and -3/2 are zeros, which is what we found by hand already. And you'll notice that -7/4 is a minimum here, which hopefully should make sense that a minimum in the first derivative, that means that the second derivative was 0 and changed from negative to positive, which is what we found when we took the second derivative. So if the first derivative has an extrema, then our second derivative is going to be 0 and change from negative to positive. So it's going to have a point of inflection. Now, eventually, and this is something we'll practice over the next couple days as well, and you'll get some practice problems on, is that I could take this away and just give you this derivative and ask you questions about the function. Where is there a maximum? Where is there a minimum? Where are we increasing? Well, we're increasing everywhere where that's positive. Right? First derivative needs to be positive. So we'll be looking for everywhere that that is positive. That's from negative infinity to negative 2 and negative 3/2 to infinity. Where's there a maximum? Well, there's a maximum when we're changing from, this is changing from positive to negative, because that tells me we're changing from increasing to decreasing. So I should be able to give you this picture and have you tell me from this picture, where's there a max, where's there a min, where are we increasing, where are we decreasing? Or even, where are we concave up, concave down? We're concave up, where the second derivative is positive, so that means that's where the first derivative is increasing. Because first derivative increasing means the derivative of that will be positive. So that's another place that we're headed and going to be starting to look at. It's not just with a function, but with a picture. Here's the derivative. Answer some questions. That's a pretty common AP question, is it gives you a graph like this and then asks you a bunch of questions about it, about the original function. All right. Let's do one more. Next example. We want all the same information. Y prime, 2x to the 1/5. Okay, so that's going to be, the 1/5 is going to come out in front. So 1/5 times 2 is going to be 2/5. X to the, well, subtract 1 from the exponent. So 1/5 minus 1 is going to be negative 4/5. Derivative of 3 is 0. So we want to know where this is 0 or does not exist. Equals to, since it's a negative exponent, this can go on the bottom. 5 times the 5th root of x to the 4th. That's x to the negative 4/5. So our point of interest here is at 0. Because that's a place where the derivative does not exist. Derivative is 0 or derivative does not exist are our critical points. Doesn't guarantee that it's a max or min, but it's a point we should look at, look into, and investigate here. So let's make a sign chart. Zero is our point of interest. We want to point to the left of 0, point to the right of 0. Well, to the right of 0, it's going to be 2 over 5, and then, oh, that's going to be positive. And to the left of 0, oh, wait a second, to the left of 0, if I put a negative number in here, what's going to happen when I take it to the 4th? It's going to turn positive again. And so positive to positive, no change in direction means no max or min. No maximum, no minimum. We're increasing. Domain is all real numbers. This exists everywhere. And we are increasing everywhere. Depending on the book's definition of increasing. Some other books might say that this is increasing from negative infinity to 0, union with 0 to infinity. But we'll just say it's always increasing. Decreasing, regardless of what book you have, that's never decreasing. Second derivative. Here's the new stuff. I'm going to go off of this. 2/5 times a negative 4/5, because a negative 4/5 is going to come out in front. That means we have negative 8 over 25 times x to the subtract 1, negative 9/5. So that equals negative 8 over 25 times the 5th root of x to the 9th. Well, guess what? We still care about x equals 0. That's where that second derivative doesn't exist. But this time, the sign chart is actually going to look interesting here. If I plug in a positive number, then this is all going to be positive on the bottom, which leaves a negative number on the top to make it negative. But then if I plug in the negative number, if I take a negative number to the 9th, what's going to happen? It's going to stay negative, right? That means we have a negative times 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 negative is a negative. But then we have a negative on the top, negative on the bottom, positive. Okay. So we do have a point of inflection. At 0, plug in 0, we get 3. So we are concave up from negative infinity to 0, concave down from 0 to positive infinity. See if you can think about and visualize in your head before I show it to you what this graph is going to look like. We hit a point where the derivative doesn't exist. Think about what that means. We also have a point of inflection at 0, and then go from going concave up to concave down, but we're always increasing. Bam, there it is. So the reason the derivative doesn't exist at 0 is because we hit a vertical tangent line. Vertical slope is undefined. Always increasing. But then here's our point of inflection. We were going concave up, and then we changed to going concave down. We're increasing even more and more and more and more and more until we can't possibly increase anymore, hit a point of inflection. Now we're increasing less and less and less and less. But we never hit a maximum where we somehow change to decreasing. It's just increasing less and less, concave down. So that's our graph.